We are live, sir.
Okay. Hello, friends. Uh, this is Mr. Sarvesh Vazurkar. Today, I'm going to explain you about. This is the sixth session for Ballarpur Institute of Technology, Ballarpur AICT sponsored Prerna scheme for SC and SC students, for the computer science and engineering and IT students related to the subject programming and data structure on the topic linked list and its types. Sorry, trees and graphs. Next is what we are going to cover in this today's slide is like trees along with its various working and the graphs and the various operations and traversing's that that we are going to perform it on the graph. We'll see it in today's class. First, this is the simple tree diagram which is visible to you in this on the screen. It's a tree diagram based on a particular family where Dusty, the name of the person Dusty, which is act as a root of the family, is having two different bands. That is honeybee, Andy, so on, so forth. They are having their childrens on the left hand side and on the right hand side. They are again having their sub childrens. Each and every terminology I'm going to explain it to you in this today's class. First is the Dusty, which is act as a root of the tree from which the tree diagram has been started. The root of the complete tree diagram is with Dusty, where at the bottom line, all the names, those who are there in the gray color, they are called as the leaf nodes. The leaf nodes are the nodes, have not, those who don't have any children's or any other child nodes with them. That's why they are called as leaf node. What are the other nodes? I'm going to explain. First of all, what is the definition of a tree? A tree is a finite set of one or more nodes, such as there is a specially designated node called the root. Just now I have explained what is the root, how the root specifies in a particular tree. The remaining nodes are partitioned into where n is greater than or equal to 0, some disjoint sets, that is various subtrees I can say, T1, T2, T3 up to Tn, where each of these set is a tree. For example, honeybee is a T1, brandy is T2. They are not joined with each other. They are disjoint with each other, but they are having with their own other family members of that tree. We also called as this honeybee, brandy are the subtrees of the root. This is the root, that is dusty. Honeybee and brandy are the subtrees of the root. What is the level and depth of the tree? Where, see, for example, in the given diagram, there are 13 different nodes up to M, from A to say M. A is having three different child, that is B, C, and D, where A is at level 1, B is at level B, C, D are at level 2, E, F, G, H, I, J are at level 3, and K, L, M are at level 4. Most important, the degree of node. Second, that is the degree of node. The degree of node is means the node who is having the number of childrens are called as the degree of node. For example, over here, A is having how many children? A is having three different children. Those are at level 2, but A is at level 1, doesn't matter. Every single node is having a degree of that particular node. A is having three nodes. That's why the degree of node A is 3. Same thing, the node B, they are having two nodes. Degree of node B is 2. Degree of node C is 1. Degree of node D is 3, as the node D is connected to D is having 3 different childs. That's why the degree of node D is 3. Same thing if we go with the other next level, that is 3, level number 3, E is having 2 childrens, whereas F does not having any children, so the degree of node F is 0. Degree of node G is again 0. Degree of node H is 1, as if H is having 1 children, and uh, and I is 0, J is again 0. Same thing, the nodes who does not have any children are called as leaf nodes. Called as leaf nodes. Siblings are the nodes, those who are of same parents, called as sibling. The highest degree of node of any different node in a tree is called as the degree of the tree. Is called as the degree of that tree. The level of the node, height of the tree is same. That means whatever the number of levels are there, that will be the height of that tree. Various terminologies that I have just now discussed it with you. The degree of node is the number of subtrees of the node, where the degree of A is 3 and the degree of C is 1. The node with degree 0 is the leaf or terminal node, where the node has that has subtrees is the parent of the root of that subtree, where the root of this subtree are the children of the node, and children of the same parents are the siblings that I have just now discussed. The ancestors of that node are all the nodes along with the path from the root node, from the root to that particular node, that called as the ancestor. Then the representation of tree is like we can represent the tree by using the link. This is the link representation of a tree, where B A is a subset of B, E, K, L, F, C, G, and so on. The root comes first, followed by the list of subtrees. A is the main root, I can say, whereas B is over there on the left hand side. E is the subnode of B, subtree of B, and E is having two children, that is K and L. Same thing, B is having two children, E and F. A is having B, comma C, which is having 1, D is having again, and so on. The same tree diagram can be represented by using this link representation. Exactly like this, the data link, and link 1 2 3 up to n number of links, I can say. Left child right sibling. Left child right sibling. For example, see, if A is the root node, it is having the child that is left on its left, that is B, and B is having two childs, they are E and C. E is again having one child, that is F. K is again having one child, sorry, E is having two childs, that is F and K, and K is having only one child, that is L. C is one, that is G. D is having H, I, J, and M, and so on, like this. Same, the next concept and the most important concept related to tree is binary tree, where a binary tree is a finite set of nodes. The definition of binary tree is very simple. Binary tree is a finite set of nodes that is either empty or that consist of a root and two disjoint binary trees. Consist of a root and two disjoint binary trees called as the left subtree and the right subtree. Any tree that can be transformed into a binary tree, that is, it may be by left child right sibling representation, or the left subtree and the right subtree are distinguished over there. Same thing is like this. That same diagram I have explained it in the last slide. The abstract data type of binary tree, such as where the struct binary tree is objects, a finite set of nodes either empty or consisting of a root node, that is left binary tree and right binary tree. The functions are like, for example, for all binary tree 1, binary tree 2, those who are the subset of binary tree item which is belongs to the element, and so on. This is the sample tree which we are very interested in. Skewed binary tree is one of the type of binary tree. Skewed means, see, as if we have just now seen the definition of binary tree. Binary tree does not carries the childrens more than 2, at most 2. It may be 0, it may be 1, it may be 2. That's it. In that case, in that case, the complete binary tree is on the right hand side, where every node except the leaf node, every node except the leaf node are having maximum number of nodes in binary tree. The maximum number of nodes of level I minus 1 where all I or every I is greater than or equal to 1. That can be proved by induction. It is simply like binary tree of depth k is 2 to the power k minus 1 where k is greater than or equal to 1. That can be proved by induction. It is simply like, yes, the question was, that's why I have kept it in red. The question was came on that particular topic related to binary tree in gate. Within the limit I is equal to 1 to k, 2 to the power I minus 1 is equal to 2 to the power k minus 1. By which method it can be proved? It can be proved by multiplication, it can be proved by induction, it can be proved by division or number of leaf nodes and the nodes of the degree, that is 2. For an any non-empty binary tree, if no if no tree is having the number of leaf node and n2 is having, sorry, n0 is the number of leaf node and n2 is having the degree 2, then n0 is equal to n2 plus 1. That means number of level plus 1 will be the degree. For example, this is the simple example that's n is equal to, sorry, let n and of nodes and various branches in that t. Let n0, n1 and n2 represent the nodes with no children, single child, and 2 children respectively, as if the property or the characteristics of binary tree says that every node should not exceed more than 2 children. At most 2 children will be there. What is that at most 2 children? It means that uh, the tree or the nodes, they should not have more than 2 children. It may be 0, like as said over here, it may be 0, it may be single child, it may be 2 child. It belongs to the binary node. Full binary tree versus complete binary. There are two different diagrams of this graph. Let me complete binary last level does not have any children. Rest all the different neighbor except the last level have exactly 2 children. The word is very important. Have exactly 2 children. If each and every node except the leaf node in the last level should have 2 nodes, exact 2 nodes, called as full binary tree, and the nodes which are having which are having two two child nodes, they are called as the complete binary tree. In other words, I can say like full binary tree of the depth k is a binary tree of the depth k having 2 to the power k minus 1 node. where k is greater than or equal to 0, like this. And the binary tree with n nodes and depth k is complete if and only if its nodes correspond to the nodes number from 1 to n in the full binary tree of the depth k. Binary tree representations is like this. You can use parent, you can use left child, you can use right child as well. If a complete binary tree with n nodes, that is depth is equal to log n plus 1, is represented sequentially, then for any node with index I, where 1 is less than or equal to I, is less than or equal to n, where n is any number of node, where n is the number of node, I can say. Next is sequential representation, like this. A in terms of binary tree, we can always assume one is left node and another one is right node. In terms of sequential representation, wastage of memory will be there. If I'm going to perform the insertion operation over there, I can firstly insert it A. On the left of A, the pattern will be like this: root, left and right. The pattern will be like this: root, left and right. The same thing, A, I'm talking about this left side diagram first, which is a skewed matrix, skewed tree. A, on the left of A, there is B. On the right of A, there is nothing. That's why I have kept blank over there. Then come back to the left side, left subtree, left side. That is, on the left of B, there is C. That's why I have written C at fourth point. On the right of B, there is nothing. Same thing we have already missed at level 1, at level 2, one element which does not having any node on that side. So again we can consider two childs over there. So 6 and 7 are again remaining blank. Then we came at the left hand side of C again at next level, that is level 3. Again it is having only one children, that is D, and so on. Everything like this, it will be in the multiplication of 2. Ultimately the E will be at 16th position. On the right hand side, insertion and delete the sequential representation is like this: A, B, C. On the left hand side again of B, there is D, then E. On the left hand side of C, there is again F and G. Left side, the next element that comes into the play, that comes into the stack, is like D, and D is having two different children, that is left of D there is H, and and right of D there is I. So G, H and I are the elements that are sequentially entered in the given list. Link representation is like simply the type DEF struct node, where tree pointer is the type DEF struct node integer data, and tree pointer having left child, right child, so on, which is like this: left and right, and there in between these two there is one data called as middle. There are various different tree traversal techniques. We can consider it as left, visiting and right. L, V and R stands for moving left, visiting the node and moving right. 6 possible combination for traversals are like this: left, then visit, and then right node, left, right and then visit the node, that is root node, then root node, left, right, root node, right, left, root, uh, then next is right, root, left, right, left, root as well. To adopt the convention, we traverse left before right only. 3 traversals remain. We can use only this one, that is left, root, right, left, right, root, and root, left, right. That's it. That we can be we can use that we with the help of the another word or another synonym, I can say as root. We can traverse by using 3 different techniques, that is in order, pre-order and post-order. We can see one by one in a for a best possible way over here. First is arithmetic expression using binary tree. where the in order traversal is like this. In order means left, root, and then right. The extreme left element is like A, then its root is V, is division, and then on the right hand side it will be B. Next is it the whole part is the left side of the multiplication. That's why multiplication is the rule for is the root for A divided and B. That's why the whole part gets multiplied by that root, and on the right side, that is C. Then whole this part is the multiplication of the D, and that is the root of that D and multiplication. That's why the second multiplication comes into the play. And the main root is plus, and on the right side of plus there is E. So plus and write E. Same thing we can also go with the pre-order, that is root, left and right. Prefix is like post order, same thing we can use. Post order means left, right, and then root. Likewise, postfix expression is like level order traversal. It means from the top of the tree diagram, we can always search level wise as well. After that, in order traversal, void in order. This is the simple pseudocode for the same. Recursive version is like this. Post order traversal and pre order traversal is like this. So in that post order, we can say that pointer left and child, pointer right child, and then the main root. That means left, right, and root. In pre order, first is root, then pointer left, and then pointer right. That means root, left, and right. This one is left, right, sorry, left, pointer, and right. That is in order. This in pre and post stands for the root node. You can definitely connect it with the root node as well, where post stands for the root will come at last. First A, first left, then right, and then root, like this. Iterative in order traversal is like this. Simply like using stack, we can use this pseudocode. The whole time complexity for this is order of n. Trace operations of in order traversal is like this. You can also go with this particular technique while traversing in the tree diagram, but we can definitely follow the traditional way of traversing in the tree diagram that we have already studied right now. Level order traversal is simply like traversing the tree in the level, right? You have to start it from zeroth level, that is root level, and from that root level you may go in the you may go in level by level to complete all to traverse all the elements in the given tree diagram. This is the simple pseudocode. It is also possible to copy the binary trees as well, where the pointer can copy three different pointer, tree pointer, that is temporary, where temporary is equal to tree pointer, which can allocate the size of the memory. If it is full, if the memory is full, then it is exit. Otherwise, it may go in another way in a next line. Next is equality of binary tree. It can also be done with the help of this particular pseudocode. It may be there may be the possibility of left data which is equal to the right data. uh, the data which is the node which is present on the left side, which is exactly same as the node which is present on the right side. Traded binary tree, data structure for traded binary tree, and so various number of trees as well. Propositional calculus expression. A variable is an expression. Of course, we all know that if x and y are expression, then negation of x is and comma x and y, x or y are the expressions which we can perform it on the variable x and y. Parenthesis can be used. Of course, if we are in the data structure, parenthesis really plays a very vital role, like this. 2 to the power n possible combination for n variables. The number of nodes can be that number of possible combination are available in terms of the node in order, pre-order, and post-order as well. Post order, that is void post order, that is evaluate the tree pointer node, which can be modified the post order traversal to evaluate a propositional calculus tree. If node post order evaluation, that is node is greater than left child, post order evaluation node is greater than right child as well. In that case, it the node which is greater than the root node, the value which is greater than the root value will be on the right hand side of that root, and the value which is less than that root node will be on the left side of that root node. Ultimately, you can prove the value which is greater than the node which is greater than the particular value, then it is fine, that it is true case, otherwise it is false. If false, we can go with the left direction. If it is true, we can go with the right direction. Threaded binary tree. There are too many null pointers in current representation of binary tree, where number of nodes, n is the number of nodes, number of non-null links, that is n minus 1, and total links, that is 2n. Null links is equal to 2n minus n minus 1. That minus minus gets converted into plus, and the answer is n plus 1. Replace the null pointers with some useful threads, and that threads are nothing but, if we are connecting, if we are joining all that threads in a proper way, that threads are nothing but threaded binary tree. This is the thing. If pointer points towards left child, and if it is null, replace it with the pointer to the node that would be visited before the pointer in an in order traversal. As you know that in order traversal carries in order traversal, having the characteristics of left, then root, then right. In this particular way, you have to insert a new element in that threaded binary tree. Second one is like, if the pointer right child is null, if the right child is null, in that case, replace it with the pointer to the left node, and that would be visited after the pointer in again an in order node, in order traversal. This is the example of threaded binary tree. Like root is the root, and on the left side there is B, and on the right side there is A. Again, we want to connect all these nodes in a proper order, that is in order. In order follows the category of left, root, and right. And in this manner, we can insert and we can add the element into the binary tree called as threaded binary tree. Next is data structures for threaded binary tree. One is left thread, another one is left child, data, right child, and right thread. These are the 5 different parameters where we have to go accordingly. You can use that link way to represent the tree in a threaded way. That's why we call it as a threaded binary. If we are going to store any particular data, it directly means that it also requires certain amount of memory to store the operations which we are performing on the data structure as if it is a tree. So it is possible to perform the to utilize the memory for that threaded binary tree. How the memory representation will be there? For example, we have to know distribute the category of a threaded binary tree in these 5 different parameters. If right child is there, then it is false. If left child it is there, it is true. Which is less than the data, of course, the less than the main data. And likewise, false condition, this 5 different parts, the main node, it can be converted, can be distributed it into. The meanwhile, at the center there is a data. This part on the left hand side is for left child, this part is on the right side, the right hand side is for the right child. And then the conditions are like this: it may be false, it may be true. Accordingly, this whole part definitely requires some memory allocation. So memory is again required for the same. Next, of course, memory should be done in terms of 2 bits per node. Threaded pointer, that is unsuccess. If it is in success, then threaded pointer tree, threaded pointer temperature. Temperature is equal to tree, which is right child if tree is right threaded while temp is left threaded, and so on. In order traversal of threaded binary tree is like this. It requires the time complexity of order of n. Inserting the nodes into the threaded binary tree can again be possible in threaded binary tree. That is, insertion of nodes is possible in threaded binary tree. How to insert the nodes in threaded binary tree? There are these are the conditions to insert the nodes in the threaded binary tree is like this. You have to follow all these type of conditions. First is insert child as the right child of the as the right child of the node parent. Change parent if greater if it is greater than right thread to false. Change set child which is left thread and child which is right thread, it's true. Ultimately, set child which is less than or equal to left child to point to the parent, then and only then it is right. It is perfectly placed. Same thing is deal with the right side. If it is greater than the root node or the parent node, then it is placed. It should be placed at the right side of that root node. The examples are like this. Insert a node D as a right child of B. That is the target. You cannot insert it rightly from the root. You have to go with the root first, then A. Then on the left of A, there is no any child. On the right of B, sorry, on the right of A, there is one child called as B, because B is again having two different, sorry, B is having one children already, that is C. But we have to add D. So definitely, we can definitely add the node B, sorry, the node, new node, that is D, on the right side of B. So ultimately, B is the parent. C and D are the childs of B. B is the child of A, and A is the child of, say, a root node, which is not denoted over there. Same thing. I have just now explained this particular example. Right insert this particular part is called as inserting a node. Uh, and then there are again this next part that comes into the play again. It's like right insertion in threaded binary tree. Insertion can be done in both places. In both places, it may be right, it may be left as well. So right now we have gone through the left child, left insertion. Now we'll go with the right insertion in the threaded binary tree. The right insertion is like this. Threaded pointer, that is temperature, where right child is equal to the parent right child, and child to the right thread, that is parent, which is greater than right thread, and so on. Accordingly, if you follow this particular condition, the node which is less than the root node should be placed on the left side, and the node which is greater than the root node should be placed on the right side. That's it. Heapify the tree. Next part is heaping of the tree. That heaping of the tree is nothing but a maximum tree. Max tree is a tree in which the key value in each node which is no smaller than the key values in its children. Each node key value, we can also replace that key with the word root, is no smaller than the key values its children. Maximum is a complete binary tree, that is also a maximum tree, or we can say it as mixed max tree. Next is min tree. A min tree is a tree in which the key value in each node is no larger than the key values in its children. A minimum heap is a complete binary tree, that is also a minimum tree as well, where operations on heap are can be performed is like creation of an empty heap. Empty heap is directly means that no any element, no any node, no any tree. The whole tree structure is empty, called as empty heap. Insertion of new element into the heap is again possible to its appropriate position, of course. Deletion of the largest element from the heap can again be possible. These three operations can be performed in this heap tree. The property you need to rectify, the root of maximum heap, that is minimum heap, contains the smallest, max heap uh, that contains the largest value, which is the smallest, and it can be replaced with the word minimum heap that contains the smallest value. The root, if the root is having maximum heap, that contains the largest value. If the root it contains the minimum heap, that contains the smallest value. That's it. The simple heap means is like this, where you can go with two different parts. One is where the root node is having less value, that is 2 on the left, that is 7 and then 4. Ultimately we can shift it accordingly. So 10 and 8 and 6, that can be shifted in that particular manner as well. ADT, that is abstract data type for maximum heap, is simple. Structure for maximum heap objects is like a complete binary tree of n is greater than 0 elements organized so that the value in each node is at least as large as those in its children. For all heap belongs to maximum heap belongs to element n, and then maximum heap can create the maximum size, of course, by creating an empty heap that can hold a maximum of size of maximum size elements. Boolean heap can also be possible, that can return true else return false. Boolean heap empty, that can also return false if n is greater than 0. If there is no any space which is required to insert or delete any element from the heap, from the tree, it can show that heap is heap full. Where heap empty can also be possible, cause if there is no any element remaining in the tree, and you can perform the deleting operation. What are the various applications on tree of tree? Applications of tree are priority queue, where machine service can be there, where factory, that is time tag, amount of time, that is maximum heap which is required, and minimum amount of payment, that is maximum heap, again it is be possible over there. In terms of data structure, we can say that unordered linked list, unordered array, sorted linked list, sorted array, and heap will be the part of tree. In that case, the time complexity for insertion and deletion I have mentioned over here. If the tree is unordered, the time required for insertion it is order of 1, time required for deletion is order of n. Whatever the number of elements are there, that's why the time which is required for deleting operation is applicable, and it depends, it varies with the help of the number of nodes available in the given tree. Unsorted linked list, sorted array, sorted linked list, and maximum heap, it is like order of log n to the base 2. And for deletion, in terms of maximum, it is again same, order of log n to the base 2. Example of insertion to maximum heap is like 20, 20, 21, and simply like on the left of initial location of new node, that we need to add on the right of 2. So heapify the thing, we can insert any element, and at last insert 21 to the heap. Heap means the max tree. Heap max heap we are going for. So ultimately 21 will be at the top, will be act as a root node, and on the left of 21 there is 15, on the right of 21 there is 20, and so on. Accordingly, it requires order of log n to the base 2. The whole pseudocode is on the screen now. Example of deletion from max heap, it is like simply if we want to remove any element we can, but that should again follow all the properties of heap tree, that the properties I have already discussed. Deletion from from a maximum heap, in which you can write down this particular code, at integer parent or child element item and temperature along temporary element, I can say like printf, the heap is empty, we can we can save the value of the element with the highest key, where any atom which is equal to heap 1 use the last element in heap to adjust the heap. Parent is equal to 1, child is equal to 2. That's it. You can consider this particular diagram, this particular principle. Parent is equal to 1, child is equal to 2. You can definitely draw any particular heap tree in any possible sector. Next, till now we have gone through the binary tree. Right now, the binary search tree. A minimum element is deleted. Deletion of an arbitrary element, it requires order of n. Search of an arbitrary element, it requires order of n again. Binary search tree where every element has a unique key. The key is non-empty left subtree are smaller than the key in the right and in the root of the subtree. Again, the same principle as if we have done in the as if we have completed in the heap tree. Examples of binary search tree are like this. You can see 20 is the root. On the left of 20 there is the value which is there. All the values on the left of the 20 are less than 20, and all the values on the right of 20 they are all greater than 20, like this. Same thing on the second tree. I can say 30. Left of 30 there is 5, and right of 30 there is 40. So and again one more element is there, that is 2. Left of 5 there is 2. 60, all the values which are, see, if 60 is the root node, on the right of 60 there is 70, and if 70 is the root, on the left of 70 there is a node called as, there is a value called as 65, and the right of 70 there is a value called as 80. All the values are greater than 60. That's why all these values are on the right side of the root node, that is 60. Searching in a binary tree is again possible. Binary search tree is again possible. We can definitely go with the traditional type of searching, where return a pointer to the node that contains the key. If the key is no such, if there is no such node, then return null. You don't find any particular node for which you are searching. For example, in the third diagram, if I am going for if I am going for to search node number 55, it is not possible to search 55 in that tree. Why? Why? There is no any node which is matching with our search node. That's why it can return null. The search is empty. Another way of searching the algorithm is like another pointer search, that is while loop. Along with that, whatever the value if we are searching, it can be compared with all the elements which are already present over there, and with the help of this we can definitely able to find that on which side the value which is located. Firstly, we have to compare that value with the root, and if the value is greater than the root, I have to go in the right side of the root. If the value is less than the root, I have to go to the left side of the root. For example, insertion and deletion can again it possible in binary search tree. I can insert element number 80, which is on the right of 40. I can again insert element number 35, which is greater than 30 but less than 40. That's why I have kept over there. Same deletion of binary search tree is again possible. You can delete any different element from the tree by shifting the values by shifting the nodes to its appropriate position. For example, if I want to delete the node 60 from the given tree diagram, it is possible, but we have to put the proper place replacement for the value 60. Say 55 will be the proper replacement for 60, and on the left side of 55 there will be 50, and on the right side of 55 there will be 70. On the left of 50 then it will be 45, and on the right of 50 it will be 52. The both diagrams are on the screen now. Before deleting 60 and after deleting 60 is like this. This is the forest of a tree, where a forest is a set of n number of nodes where n is greater than or equal to 0 disjoint trees. For example, the white diagram in the first box, if the forest is like A is which is having three different nodes, that is B, C, and D, and E and F are connected to each other, and this blue, that is G, H, and I, are again with the tree called as forest. I want to connect all this forest where I can utilize A, B, C, D like this. A is having two children in that case, B and say E, where E is again having two, that is F and G. They are at the same way. G is again having two, sorry, one, that is H, and H is again having one, that is I. Accordingly, the transform of the forest into a binary tree is possible by joining all the sub trees, that is T1, T2, T3 up to Tn, in a forest of trees. It is while traversing in that forest, the pre-order and in order is like this. If F is empty, then return. Visit the root node. If any forest is empty, then return. Visit the root node of the first tree of F. Traverse the subtrees of the first tree in the pre-order. Pre-order again be like this, where the root should be visited first, then left, and then right. The root should be visited first, then left, and then right. Accordingly, you can visit all the different nodes in the tree. Same thing, traverse the subtree in first tree in the first tree in tree pre-order, traverse the remaining tree of F, that means the forest, in again in pre-order. I have just now said to you that pre-order stands for root, left, and right. In order stands for left, root, and right. If F is empty, you can follow these particular instructions. You can definitely able to go with the in order, pre-order, and post-order of a particular tree like this. Next is array representation for a set. Array representation for a set. It's like completely in ith row, you have to note down whatever the number of elements are there. Accordingly, their parents and so on. Meanwhile, you can also add parent I is equal greater than or equal to 0. I parent is equal to I, then return I. Void union 1 integer I integer j, whatever the integer that you have already defined. It may be I, it may be j. If parent I is equal to j, then your value is same. You can definitely go with in that particular direction again. Modified union operation is again possible in trees, where if integer in temperature is equal to temporary node is equal to parent of I plus parent of j. If parent I is greater than parent j, then parent I is equal to j, or parent j is equal to the temp. Then else j is have fewer nodes. It directly means that uh, parent j is equal to I. Ultimately, we can say that j is less than the another nodes. That means j has fewer nodes, lesser nodes, I can say. If the number of nodes in the tree I is less than the number of nodes in the tree j, then make j as a parent of I. Otherwise, you can reshuffle the parents as well. Otherwise, make I the parent of j as well. This is the simple example of that same, which I have explained right now. And you may get these applications. For example, for a particular array representation, 0 is equal to 4, 3 is equal to 1, and so on. You can go with this particular way to find the in order, pre-order, and post-order of a particular tree, which we have studied right now. In terms of graph, the another part of our syllabus for today's class is graph, where we can start with first the definition. What is graph? A data structure that consists of set of nodes. Nodes are replaced over here as vertices, and a set of edges. That means a set of vertices and edges that relate the nodes to each other. The set of edges describes the relationship between the vertices with directions also given, that is called as the directed graph. There are again various different types of graph: directed graph, undirected graph, complete graph, and so on, connected graph, and so on. Formal definition of graph is like this: a graph G is defined as follows, that is, graph is it consists of vertices and edges, where V of G is a finite non-empty set of vertices. Non-empty, it means at least one vertex is also required. We can say that it is a graph. And edges E of G, that called as the set of edges, where set of edges are nothing but the pair of vertices. Directed and undirected graph. Firstly, we'll go with the directed graph, where there are no any directions on the edges are there, called as undirected graph. When the edges in the graph have no direction, that called as undirected. The example is on the screen. If there are the directions are given, when the edges of the graph are having the directions, that particular graph is called as directed graph or digraph. Trees versus graph. A simple example, a simple difference: trees are special cases of graph where vertices and edges are like this. There are 1 2 10 different vertices: A B C D E F G H I J, and edges are like this: C to D one edge, sorry, G to D one edge, D to B one edge, B to A one edge, B to C, F to E, I to H, G to I, and I to J. There are various different edges are there. If and all these edges are having the direction with them, that's why this is called as the directed graph or digraph. Various terminologies related to graphs are like adjacent nodes, with two nodes are adjacent if they are connected to each other by an edge. That means from 5 is connected to 7, 5 to 7. Path is a sequence of vertices that connect two nodes in a graph. And a complete graph is like a graph in which every vertex is directly connected to every other vertex. If you are connected with every other vertex, ultimately can say that a graph is a complete graph. Graph terminologies can be, it is like, what is the number of edges in a complete directed graph with n vertices? The answer is very simple: n to the n into n minus 1. Answer is order of n. The time, which is the time complexity which is required, is like order of n square. Simply, it's a connected directed graph where all the edges are connected with each other, all the nodes are connected with each other in a directed manner. It's a complete undirected graph where all the edges are connected with each other without direction but connected. To and fro is possible. Weighted graph, if all the edges are having certain weights with respect to with respect to kilometers, with respect to any particular value, called as weighted graph. Next is how to implement a graph. The question is so simple. You can implement a graph by using array-based implementation, one-dimensional array, two-dimensional array, and so on. 2D array is called as, is also you go with the adjacency matrix, which is always we are going to represent it in this way. For example, say 0 are the age on the left side, we have representing the edges, and on the right side we are representing the another nodes. So we can use it with the, we can go with the help of the values over there. Linked list implementation in graph is also possible. Linked list representation in graph is also possible, where we can go with this particular way. Again, 1D array used to represent the vertices. A list is used for each vertex v, which contains the vertices which are adjacent from V, that is adjacency list. Same thing, index of what the link can be represented with this particular way. Link can be explained it in this particular way. Then the question arises, what is the difference between adjacency list and adjacency matrix? The answer is like this. Adjacency list is good for dense graph. If the length of the graph, if the elements in the graph are very much more dense, we can go with the adjacency matrix. Memory requirement is like order of V plus E, that is vertices plus edges. It is equal to order of mod of vertices square. Connectivity between two vertices can be tested very quickly. It is again good for sparse graph where E is not equal to order of vertices, where edges are not equal to order of vertices, and the memory requirement are like this. That is the main difference between the adjacency matrix and adjacency list as well. This is the simple graph specification based on adjacency matrix representation. If you follow the adjacency matrix in a proper way, it is simply like this. Um, where the constant is integer null h is equal to 0, and so on. It is a very dense type of thing, as I already says that key adjacency matrix can be used when the length of the graph is quite dense. I can say it is definitely possible applicable for the dense graphs only. There are two different types of searching in graphs which are very much important, and the time complexity are again very much more important in graph with related to this searching method. One is depth first search and another one is breadth first search. The depth first search, what is the idea and concept behind depth first search? We'll see it in a brief, where the traversal as far as you can down a path called as depth first search, ultimately back up as little as possible. When you reach to the dead end, next vertex has been marked or there is no next vertex. DFS can be implemented efficiently by using a stack. Yes, the question, DFS can be implemented efficiently using, the options are stacks, queues, trees and graphs, and none of this. Stacks, queues, both, none. If the options are like this, you can definitely select a stack. DFS can be efficiently implemented using a stack. DFS is the answer is simply the pseudocode is like this. You can push. I mean, if you are going to perform the stack, definitely you have to perform the push operation in the stack. And if you can go with the pop operation, it is again possible to go to insert a new element into the stack and to remove the and to remove the element from the stack can again be possible. Ultimately the DFS, that is depth first search, can be applicable by applying the stack method. For example, say set found to false. If stack push, that means you have to start it from the vertex. Vertex means the root node. Vertex is equal to any node. For example, set found to be true. Else, if you are unable to find any different element for which you are searching for, you can push the adjacency vertices onto the stack. While you can found if right path does not exist, you can definitely write if you are unable to find any different element into the stack. Simple words I can say, in simple word I can say what is DFS. That DFS is a depth first search where it uses the stack data structure. We might traverse through more edges to reach a destination vertex from the source. DFS is more suitable when there are solutions away from the source. If we are about to reach to the solution, DFS is the best algorithm to find out how the solution it will be. Next, DFS is more suitable for the game or puzzle problems. We can make a decision, then explore all the paths through this decision. And if this decision leads to win situation, we can stop. If not, the time complexity of if not, we can no further go in that DFS way. In terms of time complexity, the time complexity of depth first search is order of vertices plus edges, that is order of v plus e. When adjacency list is used, and order of v to the power 2, that is vertices to the power 2, when adjacency matrix is used, where v stands for vertices and e stands for edges, as if we have already covered it right from the start of the presentation. Here, children are visited before the siblings in DFS, whereas in BFS it is quite contrast. What is BFS? That, as the name suggests, BFS, that is breadth first search. The simple idea behind it is you can look at all possible path of the same depth before you can go to the deeper level. That BFS is also called as level order traversal, where you have to visit level layer by layer all the nodes in the tree, called as breadth first search. It can be implemented efficiently using queue. See the difference. DFS can be implemented using stack and BFS can be implemented using queue, where we can go layer by layer like this. This is the first way. We can insert Austin first in the queue, then the next layer, that is Chicago, then Dallas and Denver, then Houston, then Washington and Atlanta, and so on. You can go with any different example as well. This is all about the way of traversing in the graph, that is breadth first search and depth first search. If there is single source shortest path problem, there are multiple paths from the source vertex to the destination vertex. Shortest path means with the help of weights, whichever the minimum path from the source to the destination is called as shortest path from that way. There are different algorithms for that. That common algorithms for finding the shortest path are like Dijkstra and Bellman Ford algorithm. BFS can use to solve the shortest path graph problem when the graph is weightless or the graph or all the weights are of same weight. So in that case, BFS can be used. Otherwise, we can go with the DFS as well. This is all about the graph traversing and trees and graph complete data structure. Uh, Sandeep sir. Yeah.
Yes, sir, just a minute.
Okay.